Okay, so just a minute or two past 4 o'clock, so we appreciate you guys being patient while we wait for any last minute guys to join us. Um, Thanks for joining us once again. Hopefully, you were on the earlier session, session 103, uh, also called Audio Basics, where we did the fundamental terms, or some of the fundamental terms in audio. So, if you didn't see that, we did record these sessions. The first two are already available. They're in the invite that we sent out earlier. The 1 p.m. session will be available later tonight. And on tomorrow's invite, you'll be able to get the link there. Steve went through some great audio basics. A reminder for a lot of us that kind of forget some of the basic rules of audio, the 3dB rule. And looking forward to the next chapter of setting the foundation of all the different terminology and things that you need to know that will enable you to go to the next level when it comes to setting up DSP amplifiers. If you're not familiar with what a dB is or a frequency or anything like that, you're going to be really frustrated when you start using the software. And that's what we're hoping to do, ease that frustration in these little modular sessions that we're doing. So we are going to continue tomorrow with session 105, and that's also part of the Audio Basics group, and that's the goals of tuning a system. So for those of you guys that weren't with us earlier, we have three very important guys on the call here. They couldn't make it, so instead we found these three guys. Instead, we found these three guys. We have Steve Teresi from JL Audio in Florida. We have Kevin Ferry of JL Audio. He's located in Pittsburgh. And we got Rob Haynes.
Hello. You got an extra R in my name there.
Very. With the beard.
I'm a little bit. Well, you're going to have to change your name, Kevin, because I'm not changing the slides. So we got Rob Haynes also in California joining us. So a couple things I want to point out to you guys. Do not be afraid to show us your lovely faces. We love to see who we're talking to. Also, we would like you guys to mute your microphones once we get started to prevent any kind of background noise. And for any type of chats or anything like that, we want to be interactive. Steve's going to ask lots of questions. Please feel free to respond, and we really encourage you to respond via the chat. Make sure that when you're responding via the chat, you're sending it to everyone and not just to Steve, so the entire group can see it. We'll be monitoring the chat also for any questions that you guys may have, and maybe I'll give out a couple of pieces of swag for those of you guys that actually make an effort to participate. Ooh. Okay, reps are not included. Okay, so
how about presenters?
Yeah. We'll see what we can do. Let me see what I got here. So rather than delay anything any further, I'm going to hand it off to Steve Teresi.
All right, I'm going to grab the ball.
Okay.
I'm presenter. I'm now presenter. Sharing his super secret stuff, or maybe just the keynote. All right, so there's that one. You guys see my screen okay?
Yes.
No?
Yes,
right,
yes.
Cool. Remember, this is interactive. So, all right, cool. So thank you guys again for joining us. I always get a little nervous when we have the words audio and basic up on the screen because I know a lot of us are seasoned veterans and that may turn people off, but just know that this is all about coming together on the same plane and then moving forward as Dave just shared with us. As we get through this session, I think you'll see why we need to take it a little slower to make sure that we're all together. As we start jumping into the more what I call headier concepts about audio, if we don't have this fundamental stuff, at least on a common level, it becomes very difficult to talk about the higher level tuning and how to really take advantage of DSP. So without further ado, we'll get into the key terms for this session. We're going to talk about things like period, wavelength, phase, and polarity, delay, equalizers, both parametric and graphic, and we'll talk about the term filter, which it's a kind of a big umbrella. So we'll jump right in and talk about a period. Period is how long it takes to complete a single cycle. As you remember from our earlier session, we count frequency in cycles per second. So period is related very closely to frequency and time. It's how long it takes to complete one cycle. And if I put this on the board, you'll see that there's a single cycle, and it takes place in a period of time. And that time in this case is 1/10 of a second. So you can kind of see the relationship there. Now, there's a formula to determine what the period is, and it's 1 over f, and f stands for frequency, which doesn't really help you just yet because you don't know what the frequency is, or do you? Actually, you could probably figure it out because when we look at the other side of this, if we add up all of these different cycles that have been put on the screen now, you'll see that there's 10 of them. And those 10 cycles take place in a period of time of 1 second. So what do we know from earlier? What frequency is this? Question, waiting for an answer.
We got 10 hertz.
Fantastic. They paid attention. Woohoo! I feel accomplished. So yes, it's 10 hertz. And if you go ahead and look at the math here, the period for this frequency, for this wave, is 1 over f. So it's 1 over 10. You do the math, it's 0.1 second. And you can see that. It's illustrated, 1/10 of a second. Similarly, the frequency is equal to 1 over p. In this case, it's 1 over 0.1. And that will give you 10 hertz. So you can see how you could go from one to the other and interchange back and forth. This will become very important as we start getting into things like wavelength and phase and things of that nature. The time aspect of frequency is very, very important and it's truly fundamental. So we built on our earlier session where we talked about frequency, and now we're working on period and wavelength. We get into wavelength. Simple formula here is wavelength is equal to the speed of sound divided by frequency. That term keeps showing up, frequency. It's annoying. It shows up frequently. Anyone grown? Nothing? No? Okay. Well, to finish this out, we use 1125 feet per second as our speed of sound. That may vary depending on where you are, altitude, temperature, all those other things, but it really doesn't matter. It's a value. It's feet per second in this case, and we're going to use 50 hertz as an example. We finish out the math, you wind up with 22.5 feet. Let me pause for dramatic effect. What you just learned is that the wavelength for a single 50 hertz note is 22.5 feet long. That's really, really long. As you go higher in frequency, those wavelengths become shorter and shorter and shorter. Wavelengths are obviously very important with regard to DSP because there's all different path lengths and wavelengths that are taking place, and we need to make sure they all get synchronized. Time and wavelength are very important. For those like Conrad that deal with the metric system, we have you covered. He was talking about Celsius earlier, and I have no idea what he meant. I know Fahrenheit. So in this case, per second, and frequency work out the same, so 6.86 meters for that same wavelength. It's the same distance, it's just expressed a different way. A couple of points of reference for you. 1,000 hertz, which is a common frequency that we use, that has a wavelength of just over a foot, 1.8, 1.125 foot. So that's a kind of an interesting number to have. And 2,000 to 2,500 hertz is approximately the distance between your two ears. So 5.5 to about 6.75 inches is the path length between your two hearing devices. And that's an interesting thing to keep in mind as we go forward and start analyzing some of this information. Next up is a challenge. Phase. It's a term that's thrown around an awful lot. And I got to be honest with you guys, this is one of the hardest things in audio to kind of express. So I always get nervous when it comes to this part of the training. It's so fundamental for everything that we're going to be talking about as we get into the higher level tuning. But it's also one of the most difficult concepts to really share with people that don't live this stuff like some of the engineers do. So I'm going to do my best here. And I'll tell you that phase is related to time and frequency. Both of them sort of combined give us the phase response. And it's usually measured in degrees. Some engineers use radians, but they're weird, goofy people, and we lock them up. So we're going to talk about phase in degrees. It's just a lot easier to deal with this. The reason why this is hard to talk about is it's very hard to visualize phase. Frequency, we could talk about waves and cycles per second, and we get an idea of what frequency is all about. So that domain, the frequency domain, is something that I think is a bit easier for us to work with. And when we work with like equalizers, as we'll talk about in a little bit, we're manipulating things in the frequency domain. When it comes to phase, it's time, and time is very hard to visualize. The best example I have in phase, well, let me get in a little bit deeper. when we talk about phase, we don't really care about each point on a phase plot or a phase trace. We don't care about any of the individual points. We really care about the relative change between points. So it's not about one frequency as an example, but it's about a whole bunch of them strung together in terms of phase. So a whole bunch of phase points become more important, but even that is misleading. The combination is less important in the comparison to another phase trace. So the example I have to try to make some sense of this is, imagine if you grab your phone and you sync it up to your audio system via Bluetooth, right? So now you have the audio streaming via Bluetooth to your audio system in your car. And you went to like YouTube and you pulled up a video and decided to play the video. The audio is going to be going through the Bluetooth. And if you've ever done this, you probably realize that the audio is not in sync with the video. It's delayed. So the video is happening and then the audio is happening later. And that delay is because of the Bluetooth. And our conversation today isn't about the Bluetooth aspect of it. It's more about the delay aspect. If you were to close your eyes and ignore the video, the audio is fine. It's not delayed at all. There is no reference point. And that's a time issue. So phase being related to time, it only really makes sense when you compare it to some other aspect of time. In our example here, the Bluetooth audio versus the actual video, there's a delay between them. So when we actually start analyzing phase, we really don't care about phase of just one left speaker as an example. We really care about the relationship between the left speaker to the right speaker, or the left mid-range to the right mid-range. To the left mid-bass. So it's all about a relative comparison. And that's why I think it's difficult, because by itself, it's almost meaningless. However, in order for it to make sense, we have to look at it by itself. So here we go. Here we see a single waveform. And as you go from left to right across the screen there, you'll see different degrees of phase, from 0, 45, 90, all the way over to 360. And each one of those points is really irrelevant. But the combination of them, as we saw earlier, does make some sense as you kind of interplay between them. So at the 180 point, you'll see that there's kind of a resting of energy. So if this was an amplitude plot, there would be 0 amplitude at that point. But you don't stay there very long. Time is always passing as you look at this graph as well. That's where the time domain comes in. So it's a waveform over time, and that's where the frequency, where the phase comes in. I think the best way to illustrate this is start doing some comparisons of a single waveform to a second waveform, so you can see how the two will work well together, or maybe not so. So the next screen here, we have a 3-volt waveform and a 4-volt waveform. And they happen to be lined up so that they're both tracking at the same point. So if you look at the right half of the screen, you'll see that they both are crossing 0 at the same point. They're both crossing 90 at the same point. They're both crossing 180 at the same point, and so on.
Shut the door, please.
So if we wanted to combine these two waveforms so that we find out how much energy we have at the peaks, what would we get if we wanted to add these up? So the 4-volt peak added to the 3-volt peak. At the peak, how much voltage do you think we have? Waiting on an answer.
Well, Andy got 7 volts.
Andy got 7 volts. Well, what did he do wrong? Nothing. He did it right. The peaks would be at 7 volts. Now, at the 0 mark, or at the 180 mark, and even the 360 mark, they sum to 0 because 0 plus 0 is 0. But at the peaks, 3 plus 4 is 4. Is 7. And at the bottom peak, where it's basically crossing the 270 mark, as you see on the far right, that's also 7 volts. It's just 7 volts in the opposite direction. So that's a alignment of two waveforms starting at the same point and traveling at the same frequency. Let's move on. Now we have the same two waveforms, 4 volts and 3 volts, but now the 3-volt waveform is shifted over in time by this, in this case, 90 degrees. So if you look at the 0 point in the center of the screen where the blue line is crossing, if you go over just a little bit, you'll see the black line crosses at 90. That's a 90-degree phase shift. And if we wanted to find out what the value was, what is the highest value we'll get? The 4-volt peak and the 3-volt peak. What's the maximum that we'll ever get? It's tricky, isn't it?
Conrad says 4 volts.
4 volts. Well, I'm glad you answered. However, it's a really difficult question. The math gets tricky, so I did my best to kind of scale it out. If we're looking at this area where the two waveforms are sort of at their peaks, they're never both at the same peak. So they're going to combine somewhat, and it's not really to scale, but in the area of X, you're going to get an increase, but that increase is never going to be 7, ever. Because the peaks, the 4-volt peak and the 3-volt peak will never, ever line up because there's a shift in time. So they'll never perfectly complement each other. It'll be higher than 4 at some points, and it'll be higher than 3 at some points. At some points, it may be 5 or possibly even 6. I don't know. I'd have to do the math. It's not the conversation that we're having today. Just know that if they are not lined up at those peaks, you will never get the full amplitude, the full potential from those waveforms because they're not lined up in time. But wait, I have more. If, in this example, we have 2 waveforms that are each 3 volts, the blue and the black are now 3 volts. And in this case, one is actually shifted by 180 degrees, but you can't see that here. I'm just telling you that. This is an example of complete cancellation. So if we took the 3-volt peak and the 3-volt peak, how much do we get? What's our total voltage?
We got a few guys, Andy and M&M Auto, that are all saying 0.
0, but I have 3 and 3. How does it get 0? You're right. It's always going to be 0 because any energy that's going up is also going down in equal amounts, and that waveform is tracking perfectly in the shape. However, they're out of time. Now, a lot of people would look at this and say that the polarity is flipped. And the example I'm going to give you, I'm going to use polarity, and then I'm going to show you in a moment how this is actually not correct, but it's great to illustrate what's actually happening and how we wind up with 0. So imagine, if you could, that you have 2 subwoofers in a box, and they're being played by one channel of an amplifier, but by accident, someone flipped the polarity. The plus is going to the minus, and the minus is going to the plus on one of the woofers. And let's just say you play a 50 hertz tone. When that tone goes through, one speaker is going to go out, and the other speaker is going to go in with equal amounts in each direction. So when you play a 50 hertz tone, you effectively would get 0, but I call BS on that. You're not going to get 0. You're going to hear something, because your hearing cannot be perfectly distanced from both woofers at the same time. So you'll hear a little bit of noise, but by all intents and purposes, it's 0. So you're really getting no bass. So you go to your EQ and you take the 50 hertz slider and you push it up. And what happens? Nothing. The speakers are moving more now, but you're still getting virtually no output because they're out of sync in time. That is what I'm worried about, the time issue. Now, we did that doing polarity, but in reality, what's happening is more like this. You'll see here that the blue waveform started 180 degrees late. So as the other one is finishing its positive motion, this one is only starting it, and they're literally going opposite each other as time goes on. Now, we often look at this as polarity because we never really see the beginning of the waveform, since the waveforms seem to go on forever. Yet, a lot of times people use polarity interchangeably with phase, but this is completely wrong. It's 2 totally different phenomena. Phase is related to time. Polarity is related to the direction. Now, I use the polarity as an easy way of illustrating what happens with subwoofers and kind of how a 0 effect can happen. And I kind of related it to time, but I have a better way of illustrating the difference between phase and polarity. So polarity is up versus down or in versus out on a speaker. And if you look at these waveforms, this is a phase shift. 2 dissimilar waveforms, right? The first half is different than the second half. And the blue one is starting at 180 degrees. And you can see here that it's not just a change in direction, it's shifted over in time and they'll never line up. As opposed to this one, where they're doing the same thing, just in opposite directions. That's polarity. If you flip the plus E and minus E, this is what you wind up with. If you shift things in time, you wind up with this. So I think that's a good illustration of how phase and polarity are different. Moving on, get into wavelength and phase, and this is where some relationships get kind of interesting. Wavelength and phase are related to each other. And if we take a look at this waveform, along the bottom I'm showing the distance. So this is kind of related to the wavelength. And you see that the blue waveform has a certain amount of length. Don't even worry about the numbers on the bottom. They're pretty much irrelevant. But it's measurement of distance. And now we have the green waveform that has a longer wavelength. And we know from earlier that this is a different frequency. It's a lower frequency with a longer wavelength. We go to the red waveform. Again, we have a longer distance. This is an even lower frequency. So if you think about it, we could put the word time on the bottom, and that would be true as well. A lower frequency has a longer period to it, right? We learned that earlier when we measured period. So we looked at that and we saw that relationship. So distance and time here are linked, and time and phase are also linked. So let's see what happens if we start adding multiple multiple waveforms. So the blue one is a single waveform, and you see that it is finishing a complete cycle at the halfway point of the green waveform. It actually can complete 2 cycles to 1 cycle. And the red ones, actually, you see it fills out. The blue one does 3 complete waveforms or cycles in the period of time that the red one took to do 1. It's an interesting relationship between those 2 waveforms. Now the green one, if we add a second waveform to the green one, that's even longer. So you can kind of see things are getting a little bit more complicated, and it's for good reason. If we start thinking about phase, the phase relationship of each one of these waveforms is completely different. The wavelengths, the period, and the phase is going to be different. If you look at these 3 different points, the blue, the green, and the red, each one of those waveforms is at a different point in its cycle at that particular point in time. And if we look over here, it's different again. So every time you're going through these waveforms, because each one of them has a different period, they have a different wavelength, and they have a different cycle to them, the phase relationship between all 3 of them gets very, very difficult to pinpoint. We are going to talk about that further down into our course, but today's session, it's really more about identifying that wavelength, phase, frequency, time. These are all very tightly interrelated, and understanding how they all work together is going to make you a better system tuner and make you take advantage of the tools that a DSP amplifier or a DSP processor is going to be able to offer to you. One of those tools is going to be delay. And when you look at delay, the name says it all. It's to make something late or how much something is late. So if Rob was late today, we would say there was a 5-minute delay. So the delay is 5 minutes, and the traffic made him late. That's what happened or whatever. So we can look at the delay as just to make something late. Now, if we can control it, we can make it late to the way we want, and that's really the goal of DSP tuning for the delay aspect, is to control things the way we want it to. Now, the reality is we care about relative delay, left to right or mid-bass to subwoofer as an example. That's what we really care about. The actual delay, again, if you had a single speaker, just a mid-range speaker, and you added 10 milliseconds of delay to it, who cares? There's nothing to compare it to. It's whatever it is, it is. You don't have a reference point. Relative delay as opposed to absolute delay. Absolute delay is really meaningless to us. We don't care. Relative delay we do care about. Move on to the term equalizer. So some things, it's something that make things equal, and some things are more equal than others. And what I'm talking about there is graphic EQs versus parametric EQs. So the term equalizer means to make it equal. It makes a lot of sense. And a graphic EQ is a more traditional version of how to make things equal. These graphic EQs, you've seen them before, either physically or at least mentally. You can picture those little sliders that have a bunch of different frequencies along the bottom. You take the slider, you push it up for boost, and you pull it down for cut. And the frequency is identified by the numbers along the bottom, 50, 100, 250, whatever along the bottom. And you can boost it up by a certain amount or cut by a certain amount. You'll see the term there, fixed Q. Most people don't know what Q is. And the term that we're talking about here, it's the shape of the booster cut. It doesn't just affect a single frequency. It affects some frequencies around it. And how many frequencies around it, and the shape of that is what's determined by the Q. With a graphic EQ, it's fixed. The frequency is fixed, and you can only adjust the boost or cut at that particular point. A parametric EQ, however, is a lot more flexible. In addition to the boost and cut, you have the ability to control the frequency. You can move it to almost any position with a lot of these processors. And you can also change the shape of the boost or cut to make it very narrow or make it very wide. So you can see with a single band of parametric, you can actually simulate what's happening with many bands of a graphic EQ. Let me just show you that real quick. Here's an example of a graphic EQ. And you see that each frequency under each one of those little white sliders has a specific frequency to it. We can push the slider up to make a boost, and we can pull the slider down to make a cut. Now, the upper graph the upper EQ that I've represented there is in a very common configuration that a lot of our customers do. We call it the smiley face EQ. for good reasons. It kind of looks like one. They boost the bass, they boost the highs, and they cut the mid-range because who needs vocals anyway? I tried my best on the bottom to make a frowny face, which is how I feel about people that do those smiles. So you can kind of get the idea what a graphic EQ is all about. Basic, easy to work with. Let's move on. This is a parametric EQ. And you can see it looks very, very different than a graphic EQ. The parametric EQ has a chart next to it that has a bunch of different columns: frequency, Q, and gain. Gain could be a positive gain as a boost or a negative gain as a cut. So we can do pretty much anything we'd like. And you learned from our earlier session that boosting, adding, let's say, 6 dB of boost is going to be asking for 4 times the amplifier power at that frequency. So you can get the idea that I'm not a big fan of boosting on an EQ. So I'm showing cut here as an example. So I'm going to focus in on this one right here. That particular slider has been centered at 250 hertz, and the Q on it is 10. That 10 is a very narrow Q. It's very focused. So only right around 250 hertz is being affected. And the cut on that looks to be about a 6 dB cut at 250 hertz. And you can see a little bit above it, there's still a cut, and a little bit below it, there's still a cut. It's just not as dramatic as it is at the center point. That's a high Q parametric EQ cut. Look at this one over here. This one is a Q of 0.25, which is a very low Q. Low Q means it's a very wide range of frequencies that are going to be affected. And if you look at that, you can see we have frequencies all the way up past 10K, 10,000 hertz at a 4 kilohertz cut. We're affecting things above 10K. You can even look down by that 250. This band is impacting it down as low as 250 hertz. This wide Q allows us to affect a huge range of frequency with a single band. If you tried to do that with a graphic EQ, you'd be pulling a whole bunch of little sliders down to mimic what we've done with just a single band here. Nothing drives us more crazy than people that say, oh, a 10-band parametric isn't enough. Oh, well, you need to know how to use that parametric EQ, because when you know how to use it, you can do so many wonderful things with a parametric that would be very challenging to do with a graphic. So that's
you can literally make your smiley face with one band of parametric EQ.
And that makes me frown.
Yeah, too.
You could actually do that, though. You could make that single band take the place of that whole EQ that we showed. Excellent point, Kevin. It does make me frown, though. Okay, moving on. The term filter. I found a definition that I thought was really good for what I wanted to share with everybody. I found a definition that said it's the process of holding back elements or modifying the appearance of something. Holding back elements or modifying the appearance of something. Well, I kind of reword that a little bit. I use it as it's a useful way to get rid of something you don't want. So what are some things that we don't want? Well, I know I love my coffee. I love good coffee. And coffee grounds get put into a coffee filter. Hey, there's the magic word. And if you think about what's happening when you make coffee the right way, you take a filter and you pour hot water over the grounds of coffee, and at the bottom is the magic elixir of life. It's the coffee that you really want. But the grounds are spent. They've done their purpose. You filtered the water through them. You wound up with the coffee underneath, and now the grounds, what do you do with them? Do you keep them? No. You get rid of them. They've served their purpose. The filter has pulled them out of things and given you only what you're looking for. I like that definition. Coffee grounds through a filter, that works for me. Some other things that are useful to have a filter on. Rude comments. My example here is Dave. You know, Dave's a nice guy. He says some really stupid things sometimes and rude comments. You just filter through all the stupid stuff he says and you wind up with a really good guy. So that's Dave in a nutshell, right? So you filter out the things you don't want and you focus on what you do want. And the last one I think is a great example. It's sunglasses. Down here in Florida, these are a way of life. You use sunglasses to filter out the lights, the rays from the sun, the UV, and the light. Now, here's a great example of the filtering process. It's not collecting the UV and the light for you to use later. It's filtered. It's gone. Your eyes are protected. You're happier as a result. You can't go back and get the UV back. It's just lost. It's like the coffee grounds. It doesn't get used again. That's what I focus in on, the holding back of things. It's getting rid of things that we don't want. So to bring that into audio terms, let's look at a high-pass filter. If we focus in on holding back elements, what does a high-pass filter hold back? I'm waiting on an answer.
Conrad says it's holding back the lows.
I love a man with a hat like that. Fantastic. It holds back the low frequencies and it filters those off, and it only allows the high frequencies to pass through. That's where we get the name, the high pass. Chatting with Rob and Kevin earlier, and back in home audio early days, they used to refer to a low cut instead of a high pass. I don't know why you would do that. It is the same thing. You're cutting out the low frequencies and only letting the highs pass through. I like my definition of holding back the low frequencies to only let the high frequencies pass through. High pass filters holds back low frequencies. Logically, a low pass filter holds back the high frequencies. But wait, we have another one. What does a band pass filter do? Bueller, Bueller, Bueller.
Conrad got it. It's frequencies on both sides. Cuts top and bottom.
Conrad's rocking it. That's because he changed his shirt too. Good man. Yes, a band pass filter is going to hold back a bit of both. It'll hold back a little on the low end, hold back a little on the high end, and basically only allow a certain band of frequencies to pass through. Hence the name, band pass. Band pass allows a certain band of frequencies to pass through and holds back the others. All right, jumping into some graphs to illustrate these points. So looking at this graph, I just want to explain what we're actually looking at. Across the bottom edge, what's known as the x-axis, we're looking at frequency. So we have low frequencies on the left and high frequencies over there on the right. Along the left side of the graph is amplitude. We know that from earlier. Amplitude is higher as you go up and lower as you go down. We're going to look at a magical, mythical speaker that doesn't exist. It's one that has equal loudness or equal energy at all frequencies, same level, regardless of frequencies. Again, this does not exist. This is just for an illustration. If we were to have a speaker that could magically do this, imagine what it would take in terms of excursion. So we all know that as we go lower in frequency, the speaker is going to try to move more. But do you know how much more? Well, let's go through it. Imagine if we had a speaker that at 100 hertz had excursion of X. And let's just say X is, oh, I don't know, let's say a quarter of an inch. So at 100 hertz, it's moving a quarter of an inch to play whatever amplitude it's playing. Now, it's equal across the entire spectrum. So as we went down from 100 hertz, if we went down one octave, what frequency would we be at if we went down one octave?
We have 50.
Fantastic. So octave, as a reminder, is a halving or doubling of frequency. In this case, we're going down, so we're cutting 100 in half down to 50 hertz. In order to play the same level, the same amplitude, the same SPL at 50 hertz as we did at 100 hertz, if we were moving a quarter inch at 100 hertz, we'd have to move 4 times further at 50 hertz. That quarter inch is now 1 inch of excursion. Can your speaker do that? Oof, that's not easy. 1 inch of excursion capability of 50 hertz is very, very hard to do, and that's to maintain equal energy. But bass doesn't stop at 50 hertz. What happens if we go one more octave below that? Factor of 4 again, that quarter inch is now 4 inches of excursion necessary to maintain the same output at 25 that we did at 100 hertz. I guarantee you don't have a speaker that can reliably do that repeatedly. The excursion capability is enormous at that point. 4 inches, one way. That's crazy. Now, back in the day, about 20 years or so ago, we came out with a driver called the W7. And the W7 was well noted at the time of having some of the highest excursion capability that you could get in a car radio subwoofer, or really any subwoofer at the time. And a lot of people thought that, oh, this is great. This speaker is an SPL speaker because it can move so far. And we learned earlier that excursion does allow us to play loud. But we often corrected people and say that wasn't really the design intent. The design intent was to be good sound quality. Yes, it had the ability to play loud, but being able to play low frequency as loud as we could play higher frequency was the goal of the increased excursion. This chart that we're showing right now is why we built in the excursion capability on the W7. And then some people like you guys come along and just play 50 hertz through it all day long and just make it crazy loud and don't even bother playing 25 hertz, and it drives us nuts. But the point is made. Excursion is there for twofold reasons. One, to play louder if you wanted to, and play lower if you wanted to. But everything will have a limit. And in those limits, the best thing to do is filter out some of the frequencies that you don't want the speaker to play, or employ what we would call as a high-pass filter. So even big speakers would benefit from getting rid of some of those low frequencies. But focusing on like a door speaker for a moment. If we were to put a high-pass filter on this at, let's say, 80 hertz, what we're effectively doing is filtering out everything below that at a certain rate. So if we take a look at this graph, we'll see that from about 80 hertz and down, we have a lack of energy. It's rolling off. It doesn't just disappear. It's attenuating. Each octave below a certain point, it's getting less and less loud. The amplitude is being decreased. And if you look at this point here, where it's at minus 6 dB, that's what's known as the filter frequency of this particular filter. From that point down, every octave below that, it'll drop 24 dB worth of output, which is significant, as we know. Remember 3 dB, 6 dB, 10 dB from earlier? Well, this is what we're talking about. 6 dB down is a significant drop already, and it's going to attenuate even faster below that. There's an interesting point slightly above it. It's this point here. It's the 3 dB down point. The 3 dB down point is the half power point. Remember, minus 3 dB is cutting power in half. This is where that comes in. That's where the response is starting to roll off. The 6 dB point is the actual filter point, and the 3 dB down point is just known as a half power point. That's how a high-pass filter would work. Now, Conrad got the answer on the bandpass filter, and this is basically what he described for us. In this case, we have a low-pass filter and a high-pass filter. One is set at 500 hertz as a high-pass. The other is set as a low-pass at 5,000 hertz. And it's only allowing that band of frequencies to pass through. And if you look carefully, there is still output above and below each one of those filter frequencies. It's just greatly attenuated compared to the center of that band. And that's how bandpass filters work. A low-pass filter just would lack that high pass and just do the same thing, only filtering out the higher frequencies. Very often, we'll call these filters crossover filters. That's actually not correct. Crossover, as the name implies, is when two filters cross over each other. Where they meet is the crossover point. In all of our examples so far, nothing crossed. So we don't have a crossover. We simply have filters. I'd ask us to try to use the right terms. I know it's hard. I know Kevin, Rob, and I always flub this, and we wind up saying crossover, and we actually mean filter. But, good idea to start using the terminology as best we can. There's another definition to filter that we talked about. It's modifying the appearance. And an equalizer is a good example of modifying the appearance. An equalizer modifies the frequency response. It modifies the appearance of a frequency response. So if you think about that, when we go back to our parametric EQ, that's exactly what we've done. Each of those boosts and cuts that you see on that screen are modifying the appearance of the frequency response. Now, if it was a measured response, it'd be a bit more meaningful, but this is just a predictive response. But you can still see what's happening with this particular filter. It's modifying the appearance of the frequency response. All right, so there's the EQ. Here's something most people don't realize, that when you modify the appearance of the frequency response, you're also modifying the phase response. It's just hard to see it because there's not many tools that you can actually see what's happening in the phase domain, which we will talk about again. But know that when you modify the appearance of the frequency response with an EQ, there's a corresponding change that happens on the phase response. And I promise we will cover that, just not today. High pass and low pass filters also modify the frequency response. And if you read between the lines, you'll realize that it's also going to modify the phase response. So far we've talked about two different types of filters, high pass, low pass, band pass, and equalizers that will modify the appearance of the frequency response and also modify the appearance of the phase response. But there's another type of filter that we're going to talk about, and that's a filter called an all-pass filter. Delay and all-pass filters do not modify frequency. They only modify time or phase response. So if you never knew what an all-pass filter did and maybe you were confused by it, I think you might have been confused because it's really hard to think about modifying only the time domain or only something that's not frequency. Most of our world lives in frequency response. We have EQs that we mess with all the time. We have bass boost, and bass is frequency, right? But all-pass doesn't change that. And if you're only adjusting an all-pass filter on a single channel without ever playing the other channel, it doesn't do anything for you. It doesn't help you because we worry about relative phase and relative changes. An all-pass by itself only modifies time. as we get into these time conversations, it gets pretty deep. And we will get into that as we get into some of the other sessions in our course. But for today, we're going to leave on a bit of a cliffhanger, and we'll be able to take any questions you might have on the topics we covered today. Now, as you've seen, the earlier session covered more basic terms, and these got a little bit more detail. Level 3 is going to take a lot of these and combine them and expand on them. So you kind of see we're building and adding. So go ahead and fire out your questions if you got them. Whoops.
Steve, I have a question.
Yes. Sure, fire away.
You clearly illustrated there the effects of putting low frequency through a smaller speaker. Yet, how come when I visit some of my high-end home audio customers, why do I still run into two-channel freaks that deny that a subwoofer is needed in their audio system? Doesn't science just completely destroy that, or?
Yeah, but who got time for science? It's much cooler to just go on beliefs, right? So let me address that. It's an excellent point, and it's something that I've dealt with even within our own company on occasion. So two-channel guys, they tend to think of themselves as audio purists. And in the early days of two-channel, when people started building audio systems, and someone says, we should use a subwoofer, the implementation method was simple. They would take the wires that were going to the main speakers, split them off, and send them to a subwoofer. So now you had the same signal going to two different speakers that each had different phase response and different behavior. And as a result, what you wound up with was very tubby, muddy, and lack of definition because they weren't actually using a true filter. They weren't filtering anything. They were playing both speakers over the same frequency range. Rarely did they use any filter. And the rare occasion that they did use a filter, they would often only use a high-pass filter or a low-pass filter. Rarely did they use both. So they never actually implemented a true crossover. They just had one filter or another filter. And as a result, the phase response got out of whack. And as we'll talk about in later sessions, that's why they didn't like adding subwoofers, because it never sounded as good as they wanted it to. Here's where the crazy thing is. Home audio people have this illusion that they have it much more advanced than those car audio guys. They couldn't be more wrong. Car audio people, from the earliest days, started using electronic crossovers or filters to filter out bass from mids and highs and mids and highs from the bass. We were implementing these things across the board way before most home audio people were doing. Most home audio people have no idea what a true proper crossover system can do for them. Now, this is a sales pitch, and I apologize, but we do offer a product called the CR1, which is one of the best electronic filters, crossovers that you can get to add a subwoofer to an audio system. Tons of adjustability, tons of control. My favorite feature is the defeat button. Because what the defeat button allows you to do, it allows you to implement the crossovers, high pass and low pass, properly, and then turn them off completely. So the sub is completely removed from the system and the main speakers are left to play full range again. When you implement it correctly, the difference is dramatic. There's a company called Magico, which makes some of the finest floor standing speakers that I've heard in a long, long time. When we did a demonstration using their speakers, the CR1 and one of our home audio subwoofers, they couldn't believe how good their own speakers sounded because we got rid of those lower octaves from really causing problem with the smaller mid-bass drivers that they were using. They were good mid-bass drivers, mind you, but they can't play 25 hertz with authority like a Fathom could or an E-sub could. And I think that is where you got your feedback that a lot of people in two-channel, hey, there's a CR1. The two-channel guys are resistant because they've heard stories about improper implementation and not proper implementation. And to those guys, I would say, get them the CR1. Let's get it into their showroom. Let's get it into their home. Wire it up and set it up, and you'll see the difference that a proper filter, a proper crossover can actually do for two-channel. It is dramatic, without a doubt. I hope that answered it.
Yes, thank you.
Cool. Any other question?
There's nothing on the chat, Steve.
Gotcha. So let me just share this with you guys. We've built quite a bit. Rob started off and he talked about our product and our tune software and how to kind of get together with that. Our earlier session today, we talked about some of the more basic terms in audio that many of us know, and maybe you have a different wrinkle on it now. Maybe you learned a little bit, hopefully. Today we talked about some of the headier terms like polarity and phase and things of that nature, and I think we have a better understanding of that. As we get into our next session tomorrow, we're going to talk about what I think is one of the most important parts of the class, and that is the goals of tuning. Very often we're very keen to get in there and start spinning dials and adjusting sliders and things of that nature without a true path of where we're actually going. So when we get into that, we're going to talk about the goals of system tuning, what the actual purpose is, what are we after. And I think from there, once we get past that, we'll talk about the tools that we'll use to get there. That'll be session 106. And then we'll talk about 2 different tuning methods, a quick tuning method and a more advanced tuning method. The tuning methods don't make any sense until we get all this other stuff covered. And hopefully our presentations today, as well as the ones we did last week, are all building and helpful to you. And just get ready because we got a lot more coming. Dave, do you have anything to add?
No, that's pretty much it. As mentioned, we have been recording some of these sessions. So if today's session, if you were distracted for a moment or was a little heavy and you need to watch it again, we'll have that available for you guys on tomorrow's registration form. There'll be a link there and you can click on that and watch it yourself. I mean, lots of obviously great content. Some of it might be, a little technical, so feel free to use that tool. So tomorrow's session is Wednesday at 1 p.m. Okay, so after that, then we'll continue the following week with the other session. So we did decide to merge in an additional session at the very end, which we're going to spend a little bit more time on MVI and the marine things. The marine tuning aspects. Sorry, I'm reading my notes here. So we originally have been talking about 9 sessions. Essentially, we're going to turn it into 10 sessions at the very end. You'll see that as part of the schedule. And make sure you register for that. And that's it. So appreciate your time tonight, guys. If there's no more questions for anybody, we will call it a night.
Well, thanks again, guys. We'll see you tomorrow.
Thanks, guys.
Thanks, everybody.